This lesson is for Chapter 4, Section 1, so if everybody would turn into their books to page 312 and get out their notebook, we will get started. So recall from the past when we talked about rational numbers back in junior high and Algebra 2, rational numbers mean that something can be rewritten in A over B form. So in this section we're going to talk about rational functions, so it's going to make sense that the rational function could be of the form n of x over d of x. Now n of x, it means nothing more special than the numerator function. D of x means nothing more special than denominator function. Again, when we have denominators and fractions and things like that, we have to watch for the zeros in the bottom because those are undefined. We're also going to be discussing the behavior of these rational functions. To figure out how the graph of a function is going to look, find the zeros of the function. Then choose a lot of values leading into those zeros from the left and leading it into from the right to get a picture of it or a graph of it. For an example of this, let's take a look at checkpoint number 1 on page 312. Find the domain of f of x equals 3x over x minus 1, and then discuss the behavior near any excluded values or zeros. All right, so when you look at this one, I think you guys can all tell that the thing that's going to make the denominator equal to 0 is a 1. So our domain will be all real values, but x cannot equal 1. Okay, so then the next task is just to build a table of points that lead into 1 and lead away from 1. So if we were to fill, first of all, leading into 1 from the left, okay, maybe we could start with 0 and then maybe do a 0.5, a 0.9, 99, 999. Okay, that would be definitely sufficient. If you punch these in, I'm just going to fill in what the table values would end up being. We also need to come at our 1 from the right. Okay, so this was leading into 1. This one is going to be leading into 1 from the other direction. So maybe we would think about 2, maybe 1.5, getting closer yet, getting a little bit closer yet, and one more last one still. Okay, I guess I could put in that these are the f of x values. So the values that we come up with here are 6, 9, 33, 303, and 3003. All right, so you can see from this, as x approaches 1 from the left, okay, x is getting closer to 1, and the f of x is heading rapidly towards negative infinity. So as x approaches, as x approaches 1, f of x decreases, and the book calls this without bound. Okay, it's going to head towards negative infinity, and there won't be any breaks or gaps or stops along the way. It'll just head towards negative infinity without bound. The approachment from the right, as our x value got closer to 1 again, look at your f of x values, they're getting higher, and they're getting higher quite fast. So as x approaches 1 from the right, f of x increases without bound. Okay, it's heading on its way to positive infinity. These behaviors have a notation that go with them. If I can get my slide to advance here. Oh, I skipped one. Hang on. Behavior of the functions as x nears a0 has a notation that describes it. So like from that last problem, okay, so if you can kind of see the notes for that one at the same time as I'm talking here, this will make a little bit more sense. But the f of x approached negative infinity as x got closer to 1 from the left. This little minus sign, this superscript minus sign, means that we're coming at that number from the left side or the negative side of it. The second line there, f of x approaches infinity as x approaches 1 from the right. Okay, so again, that superscript plus is going to mean that we're coming at it from the right. So again, that's a notation that you can find in your book, and that's what that's going to mean. Sorry here, I don't know why my smartboard won't advance. I gotta walk to my computer. Here we go. Checkpoint number 1 also had some asymptotes. Now, asymptotes are going to be lines that our graph approaches but never actually touches. And again, if you think back to Algebra 2, this term should ring a bell. Since 1 was a 0 in that checkpoint number 1, the graph is never going to actually reach it. It will near it closer and closer but never reach it. So the line x equals 1 is called a vertical asymptote. If a graph doesn't quite reach a y value, there is also something called a horizontal asymptote. In this last one, if you were to enter that function into your graphing calculator, you would see that it makes a hyperbola type shape. Okay, so it ended up doing something such like this. Now if you look, there was a horizontal line that neither of those curves on your graphing screen hit, and it was the line y equals 3 that both of them approached but never touched. Oops, that went backwards, sorry. Ugh. That still wasn't it. My goodness, hang on. Now, to sum part of this up, vertical asymptotes are going to be the zeros of the denominator, but sometimes we're going to have numerator functions and denominator functions that reduce. So you might end up with a polynomial function as a numerator and a polynomial function as a denominator. Before we go looking for those denominator zeros, we want to reduce the function if at all possible. So that might involve factoring the top and the bottom and seeing if there's any common factors that can be eliminated. That will come up in the future here in one of our checkpoint problems. Two, horizontal asymptotes may or may not exist. To find out, what we do is compare the degrees of the numerator function and denominator function. So this comes with three possibilities. If the numerator has a smaller degree than the denominator, y equals 0 will be the horizontal asymptote. Situation 2, if the degrees are the same, the asymptote's going to be the line y is equal a over b. Now a stands for the lead coefficient of the numerator function and b stands for the lead coefficient of the denominator function. Okay, so if the degrees match, take the lead coefficient of both, write it as a ratio a over b, and that becomes our horizontal asymptote line. Third situation, if the degree of the numerator is greater than the denominator, there will not be a horizontal asymptote. All right, checkpoint problem number 2. Find all vertical and horizontal asymptotes of the graph of f of x. All right, so first thing, taking a look at the denominator function. This does factor, x minus 1, x plus 1. Now, nothing cancels with the numerator function, so this particular f of x is going to have two zeros. So therefore, it's going to have two vertical asymptotes. So since this 0 is 1, x equals 1 is one of our vertical asymptotes. The 0 of this factor is -1, so x equals -1 is another line that is an asymptote for this function. Horizontal asymptote. Okay, if you look at the degree of the numerator and the degree of the denominator, both of them have degree 2. So they have the same degree. So when the degrees are the same, remember we do that a over b ratio. Now the lead coefficient of the numerator function is 5. The lead coefficient of the denominator function is 1. So we end up with that ratio equaling 5. So y equals 5 is our horizontal asymptote. Okay, so the horizontal line y equals 5 is that one. Checkpoint number 3, find all the vertical and horizontal asymptotes of this graph. Okay, now this one is one that we're definitely going to want to check. Notice that numerator function is a polynomial and the denominator function is also. So let's try factoring both of these. So the top one ends up being 3x and x, and then also a -2 here and a +3 here. The bottom will factor into an x plus 3 and an x plus 1. Notice that the top and the bottom both have an x plus 3 factor. So we're going to let those two cancel each other out. That leaves us only x plus 1 in the denominator. So -1 is the 0 that's going to lead us to our vertical asymptote. So our vertical asymptote is x equals -1. Okay, horizontal asymptote. Go back to comparing the degrees. We have degree of 2 in both cases. So again, we're going to do that a over b ratio. The lead coefficient for the numerator is 3, and the lead coefficient for the denominator is 1. So with us getting a ratio of 3, y equals 3 is our horizontal asymptote. Checkpoint number 4. Okay, so this one. I decided these last two slides were going to both be on checkpoint problems where we have to use one of these functions and find some information with it. So make sure that you're paying attention and taking notes on these two. They will crop up in the future. So this one says the cost C in millions of dollars of removing P% of the industrial and municipal pollutants discharged into a river is given by, and you can see the function there. Okay, now the range of P is going to go from 0 to 100. Okay, so from 0% to 100%, or just under 100%, I guess. So letter A first asks, find the cost of removing 20%, 45%, and 80% of the pollutants. So if we're going to do the first one, if we're going to remove 20% of the pollutants, simply put that into your cost function. Whoops. 255 times 20 over 100 minus 20. Simplifying that, you're going to get 510, or 5100, excuse me, over 80, which is 6375. Now do the same thing for 45%. That's going to end up being 11,475 all over 55, which is 208.64. And the last one is 80%. We end up with 20,400 all over 20, and that reduces to 1,020. Okay, so these are the costs to remove those percentages of the pollutants that have been discharged into a river. Okay, now part B says, according to the model, would it be possible to remove 100% of the pollutants? Well, let's just take a look at setting that up. If we were going to use this function and set that up, we'd have 255 times 100 over 100 minus 100. Well, that's going to give us a fraction with a zero denominator, which is undefined. So if it's an undefined amount, we cannot remove 100%. All right, checkpoint number 5. We're on page 316, we're almost done. It says a business that has a cost function of C equals 0.4x plus 8,000, where C is measured in dollars and X is the number of units produced. The average cost per unit is given by, now the book, and I couldn't figure out how to type this, so I'm going to add it now, called this function C bar because there was a cost within that cost. So C bar is equal to C over X, which would equal 0.4x plus 8,000 over X. So letter A says find the average cost per unit when X is 1,000, X is 8,000, X is 20,000, and X is 100,000. Let's just do a couple of these. I think we'll catch the drift. So let's take a look at X equaling 1,000. All right, so C bar is equal to 0.4 times 1,000 plus 8,000 over 1,000. That's going to simplify to 8,400 over 1,000, which is $8.40. That means at 1,000 units, the cost per unit is going to be about $8.40. Okay, let's do another one. Let's do the 8,000. So if 8,000 units were produced, just fill in the function and evaluate. We're going to get 11,200 over 8,000 equals $1.40. So now it's just $1.40 per unit. Well, let's do just one more. I think you get the pattern here. But let's just pretend X is equal to 20,000. All over 20,000. Evaluating, we're going to get 16,000 all over 20,000, which is equal to 80 cents. So 80 cents per unit now. So you'll notice that the price is going to drop per unit drastically the more and more units are produced. Okay, so look at part B. What is the horizontal asymptote for the function? All right, so taking a look at this, our top function here has degree 1, and our bottom function, our denominator function, has degree 1. So again, we're going to be looking at a ratio of our lead coefficients. So our lead coefficient for numerator function was 0.4. Our denominator's lead coefficient is 1. So that ratio ends up being 0.4 over 1, or 0.4. Now what does this indicate? This indicates C bar has a horizontal asymptote of y equals 0.4. Okay, so in other words, as the units produced increase the average cost is going to get closer to 40 cents. So if we kept upping the amount of things produced, we would get closer and closer and closer to 40 cents. Okay, so we are heading toward 40 cents per unit. All right. Well, that gave you a look at a couple of those types of word problem situations. There are a couple that I would like you to do to turn in for this one again. I'm only giving you 3. So please do and turn in 8, 17, and 44. Okay, if you have any questions, come on and see me in the morning or bring them up in class.